Good afternoon, everybody. I'm sorry that I couldn't come to UCF for the class. I had a little injury, so I hope you don't mind. Um, I'm going to record this today's lecture in two parts, and I'm going to cover two topics. And so hopefully, you can still get a good grasp of what we're going to talk about. Now, so I want to go back to the crack tip stress field that we finished talking about last lecture, right? So this is the crack tip stress field that we wrote down only the in-plane components, right? So we wrote down the full crack tip stress field, all the in-plane components and all the out-of-plane components. And I want to talk, go deeper into these expressions and, tell you the significance of this. Now, if you remember, just to show you the picture that we had before, right? So just a geometry of what we have. We have a crack here, our coordinate system, x, y, our origin at the crack tip. Now we are writing down the stress field, around this origin, right? So, at any point around the crack tip, we can, find out the three components, right? Sigma xx, sigma yy, and sigma yx. That is the plane stress components, and they are given out by here. Now, you notice that these stresses, I only, have the first term here, the first leading term in expressions. Remember, we talk about as we go close to the crack tip, all the high order terms they become negligible. And what is actually important around the crack tip is the first term, which has a term that goes inversely with the square root of r, right? So r is the distance of the point where we are finding the stress to the crack tip, right? So as we go close, that means the stress around a point very close to the crack tip. That means r is going to be small, and this term is going to dominate because the factor in front is going to be bigger than other terms. So this expression right here is only the leading term. Now we are not going to talk about the higher order terms because those are not the focus, right? So the crack tip stress field really only is a really approximation, right? Because we neglected some terms. This is not the full solution, but some significance about this is that the crack tip stress field is universal. Okay, that means that it doesn't matter what boundary conditions or loading you applied. It's going to look like this. Okay, so the form does not change. Now you have K1 and K2. These are the constants. Obviously, K1 and K2, they are not the same if you change the boundary conditions. But then the stress field expressions here, the dependence on R and the dependence on theta, they are universal, right? So it doesn't matter you're looking at a crack, like the Griffith crack, or another crack that is, instead of tension, you applied a shear on the Griffith crack, then the form is going to be encapsulated by this expression. So I'm going to show you some examples of what we mean by that. Now, so we have to finish some more things, right? So to look at actually the significance of this crack tip stress field. Now, we want to put focus on the constants, K1 and K2, okay? Now, what we want to do, as I said just now, that the boundary conditions and the loading applied, they're going to change the stress field only through K, right? So they're not going to change the expressions on theta and on R, but they're going to change what K1 is and what K2 is, okay? And so let's just dissect this a bit more. Now, we want to look at, for example, these expressions at a line right at theta equals 0. All right. Now, right at theta equals 0, let me go to this picture. That means we are at this line, right? So we're looking, the stresses that are right in front of the crack tip, right? So theta equals 0. And if you do that substitution, you're going to find out that the stresses are very simple. Okay, we have the the theta goes away, right? So theta is 0 here. You have cosine that goes to 1, and this theta for sine is going to be 0, right? So I mean this is very simple. You can just see that. So sigma xx is going to be like this. Sigma yy and sigma xy, they reduce to this form, right? So now this is very handy, very simple for us to define some terms, right? So we are really what we're looking at is here, right? So we have sigma yy, right, along the line on theta, right? And any point here is sigma xx, and then we have obviously the sigma xy as well. Now, then they are the same with respect to, they have the same expression, right? Expressed by, k over r, square root of r. Okay, now that's very good. Now we come down to the next thing that we want to talk about, which is these factors, this small k, right? So it depends then. So we can separate two types of loading that we apply to figure out what are the the corresponding k for different types of loading, because we said that the loadings only influence the crack tip stress field through k, right? So, and we found out two things, right? So the first one is that when the loading is symmetric about theta equals 0, right? So a line about theta equals 0. And if the loading is symmetric about that line, we found that K2 is exactly 0. Okay? So what do we mean by symmetric loading about theta equals 0, right? Think about the Griffith crack under tension. That is a symmetric load about theta equals. So theta equals 0 is this line, right? Right here, right? So as the pointer shows. And so if you have tension in the Griffith crack, you have basically tension, away from the crack, right? So you have here, and then you apply the force here, right? So, and then same here. This is the applied stress. Now they are symmetric about theta equals 0, right? So a case that would be anti-symmetric or not symmetric or anti-symmetric would be that you have a crack, your body is here, and then you have a shear stress that goes in opposite direction. Okay, now this is going to be anti-symmetric about the line of theta equals 0. Now, if we have the case of symmetric loading, like pure tension, pure bending, they both are symmetric, then we found out K2 is going to be 0. Okay, and on the other hand, if the loading is anti-symmetric, that means the other case that I drew right here, right, is anti-symmetric, then K1 is 0, right? For this case, K1 is 0. Over here, if we have tension, K2 is 0. Okay? And so if you think about the symmetric loading, basically that corresponds to mode 1 fracture, right? So we are pulling apart a crack with a tension that corresponds to a mode 1 fracture. Now, if we look at the anti-symmetric scenario, that is going to be in a mode 2 fracture, right? So remember, mode 2 is a shear type of loading, and then you get K1 equals 0 in that case. Now, so let's collect all these observations and summarize the crack tip stress field under these different types of modes of fracture. So let's first of all look at the in plane we have mode 1 and mode 2, right? So think about the consequence of having a mode 1 fracture, right? So mode 1 fracture, let's go back to this. Now, in the case of mode 1 fracture, we say that what K2 is 0. Okay, so the whole of this, the second part of this, the second term of this sigma xx, they are going to be 0 because under mode 1, because K2 is 0 in that case, and then we only left with this guy. Okay, likewise, the sigma yy, this term under mode 1, this term is going to go away as well, right? And over here as well, all the K2 are 0, so you're only left with terms on the first term here. Now on the mode 2, if you have applied mode 2, then it's the opposite scenarios. All the K1s are 0. So under mode 2, then you're looking at this guy here for sigma x6, this guy here for sigma yy, and this guy here for sigma xy. All right. Now I'm going to write down I'm going to have the stress fields more clearly, shown in a slide later. So basically, we have different expressions for mode 1 and mode 2. We can decompose them into different contributions from the total crack tip stress field expressions. Now this is a convenient thing, at least in the literature. We redefine the K1s. That is nothing anything new here. We're just rewriting the constants K1. Instead, we replace constant K1 with a kappa K with the subscript I, right? So subscript 1 that belongs to signifies this is mode 1. Okay. Remember that the stress field in the case of mode 1 loading, K2 is 0. So the only thing that matters is K1, and therefore in that case we write that constant instead of K1, we write big K subscript 1, and then their relation is this. So there's nothing physical about why we have to put in the square root of 2 pi here. It's just a convention we have in the when the theory was developed, so we keep that until today, and we call that K1. Now similarly, we define K2, big K subscript 2, and that corresponds to K2 square root 2 pi, and what it signifies is that now the constant is corresponding to mode 2, right? In mode 2 fracture, K1 is 0. Okay, so in expression, only the one that with K2 remains. All right, so now there are special names for this, which is a very important concept that we very central to fracture mechanics, which is called the stress intensity factor. All right, that is the second major concept that we talk about in this course. So this K1 and K2, they correspondingly refer to the mode 1 and mode 2 stress intensity factors. So I'm going to tell you a bit more about the physical significance. But before we do that, just rewriting everything in terms of the new parameter we define, right? So there's nothing new here, just a slight change in the expression, right? Instead of small k, now we write k big K1, big K2 here. So this is the forms that you're going to see very often in most textbooks. They're going to go with a big K, the stress intensity factor. They're going to be divided by 2 pi r square root, right? So this is the form that you're going to see most of the time, right? Not the small k, because we don't use the small k in the literature. Now, the stress intensity factor, what does it really measure, or what does it really mean, right? So think about the name as well. This is a stress intensity factor. Really is intensifying the stress. Okay, so this is the stress field around the crack tip, right? So corresponding to some load. So applied a certain amount of tension in the Griffith crack, right? So for example, this one right here, we apply some tension stress on a plate, and that's a crack, right? Let's say that you apply stress sigma, right, and it's going to intensify the stress. So just like the stress concentration factor, but you're going to intensify the stress, and K gives you the value of how much intensification of the stress happens around the crack tip, right? So K relates whatever stress is being applied to the stress right in front of the crack tip, okay? And that is a stress intensity factor. It is, a parameter that you can calculate, obviously, because it is based on the stress field that we found. So this is different from stress concentration factor. That's because in stress concentration factor we often talk about a feature that is not a crack. So you have a circular floor, elliptical floor around it, but the stress intensity factor, we visualize the crack as a line, right? So it's extremely sharp here, right? So this is how the difference between the two. And stress concentration factor does not have a universal expression. Okay, so it depends on what is the geometry of your a hole or a fillet, as you learn in fracture solid mechanics. But crack tip stress or the stress intensity factor, they have a universal crack tip stress field, right? That's how they were defined from. All right, so this is mode 1 and mode 2, and you just rewrite them, all of them, like this. Now, let's finish talking about the full crack tip stress field before we talk more about the how we actually calculate and what do they really mean. So we have the in-plane, which is the mode 1 and mode 2 fracture. We also have out-of-plane crack tip stress field. That corresponds to mode 3. Okay, so again, that is also an anti-symmetric loading. And so in that case, in a mode 3 fracture, the stresses that remain are the out-of-plane shear stress. So it's signified by sigma xc and yz, or they correspondingly have k3. So these two expressions I also wrote last time. So it was a solution derived by Williams, and this is the theta dependence of that shear stress, the out-of-plane shear stress. Again, we will redefine these K3 in terms of big K, and so we look at theta equals 0, the line in front of it, and then you can see that very immediately the only stress under a mode free loading, only have a component in the in sigma 2 3, right? And this is the factor that goes in front of it. And we define again, just like what we did for mode 1 and mode 2, we define a k subscript 3 that is related to small k3 here. Now that is the mode 3 stress intensity factor. Okay, so in total you have 3 different stress intensity factor, right? Mode 1, mode 2, and mode 3. And you can rewrite now the the stresses that involve K3, right? The mode 3 loading, right? So just quickly, you will see that if I have a mode 3 loading, let's go back here. If I have a mode 3 loading, which means that I'm pulling the crack in and out of the plane, right? This is the tearing mode of fracture. You will see that they don't create stresses in the plane, because you see the stress in the plane do not depend on K3. Okay, so and they only depend on K1 and K2. And K1 and K2 they only here if you have mode 1 and mode 2 loading. Okay, so the out of plane tearing mode, they're not creating these in plane stresses. Likewise, the mode 1 and mode 2 loading, they will not create through thickness shear stress, because the through thickness shear stress only depend on the third stress intensity factor, K3. Okay, so whenever we have K3, that's the only the shear in plane out of plane shear stress we're looking at, and in terms of mode 1 and mode 2, only the in plane stresses. Okay, so these are all the 3 stress intensity factor and how we define them. Now, there is one thing that you may be thinking about, or we're going to next thing we're going to talk about is that how do we use this stress intensity factor? Okay, all right. Before I do that, I just write down another way of simplifying the stress field. All right. So there are many different types of equations I'm showing you today, but So this is just summarizing what I did. If we have pure mode 1, right, the K2 is the longer there. And if you look at that, then you just got this expression right here, the K1, right? I'm just separating them, right? So if you have a combination of K1 and K2, then you have you have the summation of these two, okay? Now this is pure mode 1, pure mode 2, pure mode 3. That's just summarizing what I just said, right? So on the other hand, you can also get the displacement field, all right? So because displacement field is also part of the solutions that we derived, right? Because the area stress function from the solution of Williams, once we got that, we can actually calculate the displacement field, and that becomes very useful as well, just because you can measure displacements around the crack, and that is something you can do, and that is something you want to calculate. So I'm just showing you here, the mode 1 and mode 2, the corresponding displacements, right? So these two are in plane problems, right? So we have ux and uy here, that is in the plane, displacement in the plane. Okay, so now they are again written in terms of the stress intensity factor. So once you got the loading, and once you determine the factor Ki, stress intensity factor here, you can describe the displacement, right? So on pure mode 2, of course, that depends only on K2, and that's why we have K2 only here. And now these are in plain, 2D problems. The expressions are slightly different if you are looking at plane stress situation and plane strain situation, and they're only differing by, the constants, right? So the elastic constants. So I wrote kappa here, which appears in these equations. They are, correspondingly related to the Poisson's ratio nu. If you have plane strain, it's going to be like this. If you have plane stress situation, then kappa is this, right? So these expressions are the same, just that now kappa has changed from this. Now, so basically what you get from the crack tip stress field and the crack tip displacement field are these expressions, and then we relate them, or we express them in terms of the stress intensity factor. Okay. Now, so just summarizing what I said, of the properties of stress intensity factor. So when we got the stress field, crack tip stress field solution, the factors are not determined, right? So the solutions are all determined, except that factor, all right? And that factor, because we apply different loadings, they can change corresponding to the boundary conditions, but the stress field itself and the displacement field itself is universal. It doesn't matter what sort of crack geometry you have. And so in other words, what we really, the physical significance of this is quite remarkable, because, you don't need to think about other things when you think about fracture. Just think about what is the stress intensity factor. Then if you can calculate it or measure it, then you know exactly what happens around the crack, right? Because you know the stress around the crack tip, and that determines when the crack should go or not, right? So we can basically, the whole problem of fracture mechanics boils down to finding K, measuring K, and making sure K is not beyond what the material can resist. Okay. So this is stress intensity factor, and it has a unit of megapascal square root of meter. All right. So this is a strange unit. Okay. So this is a unit for K. So you can see it from the stress expression if you don't remember it, right here. Okay. Any of these crack tip stress field solutions, you'll be able to figure out what the unit should be, right? You have stress over here, and the only thing that has dimension is r here, right? And it goes to the square root of it. So you just take megapascal, or Pascal or gigapascal, doesn't matter. And then K3 should have the same unit as a stress quantity times the square root of r unit of that product. Okay, so this is a stress intensity factor, right? The conceptual part of it, and really derived from the stress crack tip stress field. All right, so this is an approximation. So what do we want to do with stress intensity factor, and how do we know if this is really correct? Because we make several assumptions about, we are talking about that this is only valid when the in a region where in a region close to the crack tip, right? And at the same time, it is not correct all the way to the crack tip, because at the crack tip R goes to 0 and the solution goes to infinity. That's also not correct. So there's a region where this stress field and the K stress intensity factor is valid. And so we want to do at least some comparison or assessment of the accuracy of this approximation, right? So remember, the universal crack tip stress field only is valid. It's only universal around the crack tip. Farther away, the crack tip stress field deteriorates, right? It's not going to describe any problem accurately. So one way to do this again is by comparison to some known solutions. So this is just being rigorous and all that, and this is what we do in mechanics. Whenever we come up with new solution, let's see that if how good the approximation is. Now, how do we assess that? Now we have a simple problem. I hope by now you get an idea of kind of engineering. So if we have a solution, and then let's find a simple problem and see if we can predict that simple problem correctly first. So the simple problem is going to be the Griffith problem, because this is a solution. This is a problem where the solution is, the exact solution is available, right? So English derived one solution for it. It works across the whole plate, not only at the crack tip, and then there's no approximation to it, right? So this is the Griffith crack problem, or sometimes we call it a through crack in an infinite plate. Basically, you have the plate is infinitely large, and then you have a crack, in there with stresses of tension applied on both sides. So we have the complete stress field all over the whole plate, and that is something we can do. Or sometimes these days we can compare solutions to finite element, right? But back in the days there was not. So we compare to analytical solutions. So I'm going to show you another solution, not by Inglis. It's a solution by Westergaard. So this is a slightly easier expression to work with. So we're going to see that we're going to compare that solution with the stress intensity solution. So let me write down what is the Westergaard solution. So the Westergaard solution also is quite simple, and basically, so we want to compare. We just take one stress component to compare, right? So the Westergaard. Let's look at the sigma yy, right? Sigma yy from Westergaard solution, that is going to be sigma x times x, sorry, x squared minus a squared square root, okay? And obviously, now in the Westergaard solution, the origin is defined at the center, okay? So this is the coordinate system, This is Westergaard solution. So the solution in YY, which means that we're looking at this stress, right? Sigma YY along the, in front of the crack, right? Along this line. Okay, so we're going to compare that solution to the crack tip stress field by Williams. Now, sigma YY, now X is any point that is, before that origin, right? So that is X. But that is not the same coordinate system we use in a universal crack tip stress field, because our origin is placed in the crack tip. So we just need to do a change of coordinate system by writing that R to be X minus A, right? So because in the crack tip, universal crack tip stress field, our origin is right here. And then we measure R from that point, right? So any point R here, is going to be X minus A, right? So X with respect to this origin, so any point, so correspondingly we have R equals X minus A. Now you can, substitute R into this expression. Okay, this is, let me eraser. Let me write that more properly. We have sigma YY from the Westergaard solution, sigma X squared minus A squared. Now you just need to substitute R equals X minus A into here, okay? And if you do that and do some algebra, you end up with sigma R plus A, R plus, okay, let me erase that. Sigma R plus A and R plus 2A R square root. Okay. So this is the corresponding exact solution in Westergaard, and if we can compare that now, right? So this is the stress along the right in front of the crack, and it's the sigma YY, right? So that's in that direction, and this is the exact solution. Now we should compare that to the crack tip stress solution. So this is shown here. So if we look at the universal crack tip stress field solution, right? So that is at theta equals 0. That is right in front of the crack tip, and we know that all the theta goes away, and that is the only thing that is left. That is K1, stress intensity factor 2 pi r. You can also write down the displacement. I'm writing down for you here, and this is the exact solution that we are looking at for Westergaard. So in this plot, you can see that. The solid line, it is the solution by Westergaard, and that is the exact solution, right? So that is the correct solution, and then we are looking at the approximate solution from the universal crack tip stress, and that is expressed by this line. Okay, that is the K1 2 pi r, right? So if you do this comparison, you're going to find out that as R goes very close to 0, that means that you're very close to the crack tip. You're going to get the two solutions to be very close. Okay, so that makes sense, because if you look at the solution here, you want R to be very small compared to A. Then you can make approximation on the on this sigma YY. And what you're going to get is actually this one right here, right? So if you make an assumption that R is very small and R is much smaller than A. This is the Westergaard solution, right? So the same one that are here, but then once you make that R smaller than A approximation, you're going to get this expression. So what you do is basically you look at R and A, and then when there's a sum of them, you take away the R, right? So you get this as the approximation, and if you plot both of them, they are very close here. Now, when R goes to very large, that is the other end. Now, when R goes to very large, what happens to the crack tip stress field? For the universal crack tip stress field, it's going to go to 0, right? Because R goes to very large, the term goes to 0, right? So this is just clear from this expression. Now, the exact solution, that is the Westergaard solution. Here, sorry, right? So not this one, right? This one only works when R is smaller than A. Now, this case, you want to go for R is much larger than A. Okay, so you can again make another approximation. Now, when R is much bigger than A, then you can start to neglect some terms here. In this case, you can get R is much larger than A, then you can get sigma R. You can neglect the A, and now R squared plus 2AR, that means that 2AR compared to R squared is going to be very small because R already is much larger than A. So you get you get R squared, right? And in this case, that you see that it's actually tending towards sigma. Okay, so that is exactly where this is tending towards when R becomes really large, right? And that sigma is exactly what you're applying as the stress, the pure tension you're applying to. And that makes sense because as you're going away from the crack, look at the picture here, right? So as your R goes very far, so somewhere around here, basically the plate is under universal tension of sigma, right? So it's not going to be intensified. The stress is just whatever the applied stress is, just like a universal tension with our plate. But as you go close, that stress is going to be larger than sigma because it's intensified by the crack around the crack tip. Okay, so this is the Griffith crack, and then if you plot these two together, now exactly you can now equate these two together, right? Because they are, as R goes to very close to the crack tip, these two expressions, very close to each other, very good approximation. So you can equate them, and in this case, you can exactly calculate what K1 is, right? So K1 is going to be sigma square root pi A. Okay, so that's basically you take this term K1. So for the Griffith crack, K1 2 pi R equal to sigma A square root 2R, right? So, and if you do that, you can actually calculate K1. Now, this can be analytically derived for this particular problem just because we already know analytically what the stress field is. So typically K1 is not you can't really get this analytically. Most of the time, again, we use finite element analysis. If we have a more complex geometry and loading, right? But for this simple geometry, a crack in an infinite plate, we have analytical solution and we can get K1 analytically. So later on in the next few lectures, I'm going to show you a bit more various kinds of crack problems that have analytical solutions. There are not very many, just a few, right? So once we we exhaust all the solutions, we go to finite element where we get actually can deal with more general and more complex problems. Okay, so this is the K1, and it's exactly sigma square root pi A. And this is for Griffith crack. Now K1 is going to be different if you change the loading, or you change to a different geometry. And you said this is K1 because the Griffith crack problem is a mode 1 fracture problem, right? The loading is symmetric about the crack. It's a pure tension. It's opening mode. So K2 is going to be 0, and K3 is going to be 0, right? So those things you can just by intuition, or by understanding the solution, you can deduce K2, K3 for those guys. For the Griffith crack is going to be 0. We only have K1. Now there's one more point I want to make about this, right? So K1 again depends on of course it depends on the loading applied, and it also has a crack length dependence here, right? Square root A. Again, this is dependence on the square root of the crack length, right? Okay, so you can tell this is also physically it's making physical sense as well. All right, A is the crack length. The square root of crack length. If you remember or recall, the square root of crack length appears in the Griffith solution. When we deal with energy release rate, it appears in English solution when he tried to find the stress around the crack tip. Now, around an elliptical floor. So a larger the A, that means the crack is larger. Then you increase K1, that means that you intensify the applied stress even more, right? And this square root of A dependence is again consistent with Griffith analysis and also English. All right. Now you can also do a compare the universal crack tip displacement, right, from the two solutions again. So Westergaard also figured that out. The displacement field, which is the exact solution. I'm not going to go through this because these are a little bit theoretical and could be a bit dry. But I just wanted to show you that once you got these solutions, you can compare them, and they should match. If not, this is one way to check your solution. The displacement is also something that is very useful because you can actually go and measure it. So if you look at the displacement solution, this is the displacement solution of the crack tip, actually behind the crack tip, right? So let me go to this picture. So when we talk about displacement, we typically don't look at displacement in front because it's hard for us to measure the displacement for a material that is not broken. We can do it now, but back in the days it was easier to measure the crack tip or the displacement behind the crack tip. Okay, so because you can just hang extensometer around the crack and the mouth of the crack, and then you measure. And since your displacement solution, you get the whole crack tip, around crack tip, you just have to set theta to be 90 degrees, 180 degrees, and then the solution for the displacement crack tip will give you the displacement here. And you can and people did go measure that displacement behind the crack tip and compare with the solutions. So these are ways to make sure your solution is correct. Now, so I am not going through the the displacement, but then you can do again the same approximation. You take R goes to 0, goes to very small, and then you compare the displacement uy, and you can plot them and see that they're going to go converge to the same line. Actually independent of what K1 is, right? So the dependence of those, is overriding as as R goes to 0, right? The factor doesn't really matter. Now, that's displacement field. Now I want to show you a different crack, right? So we've been talking about Griffith crack many times. That's because that is a simple solution that we have the exact analytical solution where we can compare to. Now this is another solution, another example that I want to show you just to show you how K1 changes. And this is not a solution that not a problem that we have analytical solution to. So this is an edge crack in a semi-infinite plate. So very similar to Griffith problem, right? This is the Griffith. You have a through crack and then tension applied. Now you just think about cutting this into half. Okay, so then you get the edge crack, same tension. Now just half of the A. Now this is a problem that is there is very little thing you can do to solve it analytically. So it's quite simple, but then in solid mechanics, it's very hard to find a solution. And in this case, the stress intensity factor is very close to the Griffith crack problem, but there's a numerical factor in front of it, right? So this is 1.12 of sigma square root pi a. Okay, so this is for the edge crack in a semi-infinite plate. So let's see, the boundary conditions, the crack geometry are different, therefore K1 changes, right? K1 only receive information, K1 only depends on how the loading is and how the geometry is, right? The K1 changes. Now the field around that crack tip and around that crack tip, the dependence on theta and R is the same. Only the K changes from these two. The universal crack tip stress field works around here and works around here, but just that they are different by K1. Now both of these are Mo1 problems, right? Because the loading is symmetric about theta equals 0.9. If you compare the stress intensity factor for this guy, which is 1.12, that's 12% more than the Griffith crack, right? Griffith crack is just simply K1 equals sigma, right? So this is a bit larger. And if you take a look at, this is a picture I just take from the book, right? So pretty good illustration. So instead of, this is the edge crack problem, right? So this is a free surface, no forces and no displacement applied because this is a free surface. Now compare that to the Griffith crack problem. Now this surface is held onto by the other half of the plate, right? So there are some, the boundary conditions, the conditions on this one is not the same as here, because here there's no forces, no stresses. And here, same position, but in the Griffith crack, there are some stresses to hold it. And you can see that, if we overlay the Griffith crack opening profile, right, this is the displacement solution, so we can actually plot it. And overlay that on the edge crack problem, you're going to find that the through crack does not open as much as the edge crack. Okay, and so another way of saying this is that this one in this configuration under the same applied stress sigma is going to crack first than this one, because the intensity around the crack tip is higher in this configuration, in the edge crack configuration, than in the Griffith configuration, right? The intensity is 12% more, right? Under the same loading of sigma. So this is edge crack. You can see what you can do is that what you can see you can do is to formulate a fracture criterion actually based on the stress intensity factor, because at the beginning we talked about the Griffith energy release rate, and we need to make sure that the energy release rate being applied is not more than the fracture energy, that is the fracture energy of the material. Now we have a different parameter here, which is the stress intensity factor. So what you need to do is very similar. So you want to make sure that the stress intensity applied is less than the critical stress intensity factor that the material can take, right? So we're going to talk about that stress intensity factor criterion more in the lectures later on. So this is to define what K is. Obviously, we need to find ways to calculate it, to measure it, and to formulate a criterion based on stress intensity factor K. Okay, so this is the first topic I want to talk about. I also have a little bit more I want to cover in today's lecture, which is, a relation between G, energy release rate, and the stress intensity factor K, which I'll do in a separate video.